down, and then we trap them in this standing wave of light. And these atoms can then be trapped in the sides of the what we call optical lattice. Okay, but they can also hop around, and they can interact when they meet. Okay, so this is still very quantum optical in the sense that we have atoms that react to light. We trap them through optical potentials. All of this is described by the quantum optics and the optics and the atomic physics that was developed during the 60s, the 70s, and the 80s, and so on. Even though these kind of experiments kind of started in the 2000s or late 90s. But I will talk a lot about trapped atoms and optical lattices in particular later. But let's say that this is still within the realm of quantum optics, even though we start to see something different to quantum optics, as I will discuss later, which is many-body physics. But then we come in here, and we have something like trapped ions. So these are charged atoms, if you want to call them like that. Charged atoms that you can trap spatially with electrodes and with electric fields, magnetic fields, radio frequency fields. So nothing to do with optics, even though you can still address them, as you can see there, with a laser to change the internal state of the atom. Okay, so you still have lasers, you still have atoms, but now you have degrees of freedom that are not very quantum optical in the sense that these atoms that are trapped, they have the motional degree of freedom, and that's actually how they communicate. So when one atom moves, because they are charged, through Coulomb interaction, they can sense each other. And that's the interactions that you have between them. So this is no longer, let's say, quantum optics. Okay, this is beyond quantum optics in the sense that you have Coulomb interactions, and then you reach types of models that are not typically studied in quantum optics when it started. Yeah, then you have a whole field of mechanical motion driven by light or electromagnetic fields in general. That doesn't need to be light. It could be other type of electromagnetic radiation, in which, for example, you have a mechanical element that reacts to light. In this case, you have a mirror, okay, that can oscillate, and when light pushes into it, it moves. Okay, and then you have a connection between the light field and the mechanical element, the motion of the mechanical element, through this optomechanical coupling, we call it. Okay, so again, in here, we don't have the traditional elements of quantum optics. We don't see atoms. We don't see only light. But we really have a macroscopic or mesoscopic mechanical element that is reacting to the photons that impinge on it. Okay? And then finally, we have something that are nowadays very fashionable because they are the building blocks of quantum, the most advanced quantum computers, which are superconducting circuits. And in here, we don't have anymore anything that resembles an atom, I mean physically, or light, okay? Here, we are talking about circuits, 100% circuits, but still, I will introduce them later in more detail, but still, you can apply all the tools of quantum optics, theoretical tools of quantum optics and experimental tools to this kind of system, okay? So this is just to convince you that somehow this old-fashioned description of quantum optics as the quantum description of light-matter interaction, I think it's a little bit outdated. And then I like more to talk about quantum description of low-energy systems under open and non-equilibrium conditions. And this is actually what is common to all the systems that I showed you. Okay? They are systems that are low-energy systems, so you don't have to use, let's say, fundamental theories or high-energy physics. But the most interesting thing about these systems is that they are naturally open systems that work under non-equilibrium conditions, and you will understand why in a second. Okay? So in particular, when I say open, I guess that most of you understand, but let me define things. So when I say open, I mean that the systems, they exchange energy and information with their surrounding environment. So this generates dissipation, but also allow us to monitor the system, to drive it from outside, and to do many things on the system. And then by non-equilibrium, what I mean is that we can, since we can feed energy from the outside, we can create an imbalance between gain and loss at will. So this means that the system is no longer at thermal equilibrium. That's what we mean by non-equilibrium. It's not at thermal equilibrium, okay? We can drive it to states that are not accessible at equilibrium, okay? And this is part of what we will talk about today. So I like sometimes to just kind of encourage you to have at all times this simple picture in mind in which we have an optical cavity that is our system. Maybe inside the cavity there is matter, there is whatever you want interacting with that system, and altogether it's our open system. And the system is open because we can drive it from the outside with laser light, for example, through a partially transmitting mirror, and we can observe it. So we can monitor it, okay? All the light that comes out of the system, we can monitor it. So then it's in contact with an environment in which even the observer can be there, okay? And we have a whole apparatus of theory to describe this kind of setting of open systems, monitoring, driving, and so on, okay? Okay. But then this means that you are living a very nice time in your quantum life, which is the time in which quantum optics has grown into a very multidisciplinary field, that it's working in full synergy with other areas of physics, and in particular, one that it's very important for this Congress, which is the quantum information and technology area, okay? But also with the connection I will be focusing on today is complex systems, okay? Complex systems typical from condensed matter physics and things like that. So just to give you an idea of the type of things that we do in our group, here I have put some of the things that we work with in these topics. So related to quantum optics, we work on the quantum properties of light, so in particular generation of states of light, quantum states of light, and the manipulation of atoms, okay? For quantum information and quantum technology, if you go up, we have quantum sensing, communication, the transition from the classical world into the quantum realm or the other way around, okay? And then it's very nice the connections that we have between them, okay? Because quantum optics provides kind of the experimental platforms where to implement quantum technologies, but at the same time, the theory of quantum information provides all the mathematical tools to characterize the quantum states of light and atoms and so on, okay? And similarly, quantum optics provides the platforms and let's say the driving ideas for simulating complex systems that we cannot have in the lab easily, or we cannot access in the lab easily in the form of condensed matter. But at the same time, the world of complex systems has kind of provided us with this idea of phase transitions, of phases of matter, or many-body phases of matter, and in particular applied to quantum optics, this concept of quantum phase transitions or dissipative phase transitions that I will be focusing on today. So actually what I will tell you about today the most, it's about this idea of quantum simulation and about quantum phases of matter and a little bit about quantum phase transitions. So maybe the first thing that I like to explain, usually in this setting, is how is it possible that two things that are so different are connected? So in particular, complex systems or condensed matter, usually in these kind of problems, one is interested in systems that have an infinite number of degrees of freedom, so an Avogadro number of particles, okay? One doesn't care about the microscopic details, just some statistical observables or macroscopic observables, okay? And usually these systems are studied at equilibrium, okay? Thermal equilibrium, and that's it. And like I mentioned, quantum optics is kind of radically the opposite side of science, right? So we have few degrees of freedom that we can manipulate very easily, very precisely. So we have a lot of control over all the degrees of freedom, okay? And it behaves quantum mechanically at all levels, all the degrees of freedom. And these are not systems that are at equilibrium, but that they are open, driven, and brought out of equilibrium. So then, why are these two fields that not so long ago, maybe just a few decades ago, were completely disconnected? Okay, why are they now so much connected? This is through the idea of quantum simulation. Because at some point, people realize that there are things in condensed matter, in particular models of condensed matter, and also other complex physics fields, that are very hard to solve, or even hard to implement. So we have a model, but we cannot take condensed matter and do the condensed matter in the way that our model is implemented in there, okay? So we realized that using quantum optical systems, where we have a lot of control, we kind of can engineer specific, hard-to-solve many-body models, okay? And then try to observe in the lab how the system behaves and so on, okay? And this also came thanks to the idea that at some point it was clear that when quantum computers and all these ideas were feasible in the lab, people had to scale up the number of elements, quantum optical elements, that we had, okay? So then naturally, people started studying quantum optical systems in which now there is not only one cavity, but we want to put a number of cavities together. And then very quickly, we ran into the type of problems of many-body physics, where we have many elements, okay, interconnected. So then somehow we can connect these two worlds through these kind of ideas. And let me give you specific examples. So here I am going to discuss only one type of models. Now we are getting more into the technical world, finally, okay, in which I will start giving you the specific models that we will work with and giving you some physics. So we will be working with what I call bosonic tight binding models, okay? And let me guide you through these words. So the first one is tight binding. So tight binding refers to the fact that there is some notion of dimensionality in your system, meaning that you have many elements, okay? But the elements are interconnected in some way. For example, here, you have a 2D lattice, okay? You have many elements, and all of them are interconnected to the nearest neighbors in 2 dimensions. But bosonic refers to the fact that on every element of the system, what you have is a degree of freedom which is bosonic, which is a harmonic oscillator. So in particular, that means that on every lattice site, you can define a harmonic oscillator with bosonic operators, creation, annihilation operators that satisfy canonical commutation relations, okay? And this is what we will work with today. I will present you different models, or I will guide the physics through different models, and these models will all be of this type, represented through annihilation, creation operators, and all this algebra of harmonic oscillators and bosons that you probably know. Okay, so let me give you the canonical example within this type of models, which is the so-called Bose-Hubbard model, and that actually is the model that describes cold atoms in optical lattices that I explained you before. In particular, if you go to the red term of the Hamiltonian, you can see that that term, it tells you something very simple. It tells you if there is more than one boson at one place, at the same place, you have an energy penalty. So the energy goes up proportionally to a positive quantity that is an energy U. Okay? So this means that whenever 2 bosons meet in a place, the energy goes up. This is repulsion, okay? So you have repulsion between bosons. And you can see that the number operator there, it's n times n minus 1, so that term doesn't contribute when there are 0 or 1 particle. You need at least 2, 3, or more. On the other hand, we have the blue term, and the blue term, you can see that this refers to what we call quantum tunneling, because essentially it tells you that you can destroy a boson at position J, creating another one at position L, okay? And the sum, we perform it over the connected sites. This depends on the geometry. It could be a 1D line, and then you connect only to nearest neighbors in 1 dimension. It could be 2-dimensional, and then you have the kind of lattice that it's in the background. But in general, you could have any type of connection. And in particular, you see that let's say the tunneling rate is called J, okay? But you have to normalize this tunneling J to the number of connections of each site. So for example, in one dimension, that NC, the number of connections, will be 2, because everyone has 2 neighbors. In 2 dimensions, it would be 4, because everyone has 4 neighbors, and so on, okay? And the reason why you have to normalize it is because you want the Hamiltonians of condensed matter physics or many-body physics, you want them to be extensive quantities. So this means that if you double the size of the system, the energy should double, should not quadruple or things like this, okay? So it's just a matter of keeping the energy well scaled or well accounted for, okay? So if you don't put that J, then at some point you realize that you need it. That's the idea. But in any case, I hope that the model is clear. It has only 2 terms. But you see that there is a competition between them, because somehow the tunneling wants to spread the wave functions or wants to spread the projection of the particles onto the different states. But at the same time, the repulsion wants to keep them away from each other. Okay? So as we will see, this actually creates phase transitions. But before that, I want to show you that there are more modern systems, because let's say, as I say, these kind of systems are already touching onto 3 decades old, okay, these optical lattices, even though they are still very in vogue, because there are many experiments that couldn't be done before, and the precision that we are getting into, it's amazing. But nowadays, we can use other quantum optical platforms that are more modern, let's say, to implement the same kind of models. And this gives me also the excuse to introduce superconducting circuits that probably you have studied as well or you have read about, because as I say, they are very fashionable nowadays. But I think the story behind them is so interesting that it's worth taking a look at. So let me just give you in a nutshell what are superconducting circuits and how to implement quantum simulators of this type with them. So we all learn when we arrive to school, for some of us painfully because we don't like electric circuits and things like that when we arrive to physics, but we all learn that an LC circuit, okay, behaves as a harmonic oscillator. This is one of the first things that they tell us, and they give us a lot of, let's say, exercises about the harmonic oscillator in LC, in circuits, and so on. So essentially, we know that an LC circuit effectively is like a harmonic oscillator where you have an exchange, a periodic exchange of energy between the energy stored in the capacitor and the energy, the magnetic energy stored in the inductor, okay? So essentially, it behaves like a harmonic oscillator effectively, as I said, and they even show us that from Maxwell equations, you can do approximations and end up in this theory of electric circuits, but all of it is effective. But then, in the 90s, actually starting at the end of the 80s, but especially in the 90s and going through the 2000s, some crazy people started saying, look, if an electric circuit, it's a harmonic oscillator, cannot we make it quantum? I mean, cannot we just cool it down, remove any interaction with environment, any resistance, anything that creates the coherence, and it will behave like a quantum harmonic oscillator? So of course, many people started saying, okay, I mean, this theory of harmonic oscillators for electric circuits, it's already in the classical domain, it's already an effective thing. So probably when you go to the quantum realm, many quantum effects will appear of the particles that are moving there. I mean, it will be a complete mess. But the kind of experimentalists that are more brave, what they do is, there is a question, so let's try it. I mean, that's fine. It's fine to try to predict what will happen, but it's, in this case, it's actually nice to try to implement it in the lab. So then what they realized is that, of course, with normal cables, that's impossible because you have resistance. Whenever you have resistance, you have decoherence to the environment. You have thermal effects heating up the system and so on. But then whenever they were able to start doing experiments more and more precise with superconductors at very low temperatures, they realized that if they put in a fridge at millikelvin a superconducting circuit, LC circuit, in principle, they have what they need. So they did experiments, and then they observed the quantum harmonic oscillator without any deviation, which was quite amazing. So, well, probably you know that some of these experiments have the Nobel Prize at different stages. The latest Nobel Prize is precisely for experiments on this quantum coherency in electric circuits, in superconducting circuits. But essentially, the idea is that what the naive expectation that we could have of an LC circuit, if I just cool it down and I remove interaction with environment, it behaves quantum mechanically like a harmonic oscillator, it kind of works, okay? So this means that if now, instead of only one circuit, I put together many of them connected just through capacitors, then, of course, the energy of one can tunnel to the other. In particular, the excitations of that harmonic oscillator will be able to tunnel to the next, to the neighboring LC circuit. And that implements exactly the blue term in the Hamiltonian, okay? Now we need interactions. So interactions essentially mean in this context that the variables of the oscillators, the position and momentum, should be in the Hamiltonian more than quadratically. So that means non-linearly. So it should not be a harmonic oscillator, but an anharmonic oscillator, okay? And that we do very easily because there are not many nonlinear elements which don't destroy quantum coherence, but in the 80s, it was created. One of these elements is called Josephson junction. It received the Nobel Prize at that time. And the point is that these Josephson junctions induce nonlinearity in the, let's say, in the description of the circuit, okay, of the intensity to voltage relations and so on, induces nonlinearities without introducing any decoherence. And that's kind of the point. So once they were able to do this, that means that we can implement the red term. Okay, so putting a Josephson junction instead of a normal induction, a normal inductor, that generates the red term that we are looking for. So then, as you see, either with atoms trapped by light or by circuits exchanging excitations, so different systems, we can implement the same kind of model. And this is kind of the thing I like the most of being a theoretician. Because being a theoretician, you care about the models, but of course, knowing which kind of things you can implement in the lab drives the kind of models that you propose, okay? And the more systems that we have, the more type of different elements that we can include in the modes, in the models. Because of course, the physical processes that we can implement in superconducting circuits, apart from these two, so we can do many things like driving, dissipating, we can do many things in these circuits. That means that we have more tools, more processes available to implement models that go beyond this Bose-Hubbard. And maybe with cold atoms, for example, or with real condensed matter systems, are processes that are not possible to implement, okay? I don't have time to get into these processes because I want to give you another side of the story today. But if you are curious about the kind of processes that you can do in these systems, and both in cold atoms or superconducting circuits, we can talk about it. Okay, but what I want to talk about now, let me do a little bit of a detour, is the kind of things that we can study with these quantum simulators. And first I want to talk about quantum phase transitions. And perhaps one interesting, or the first interesting thing is to define them. Like, I think we are all familiar with phase transitions, but what makes a phase transition quantum, okay? And that's kind of the idea. And for that, first, let's talk about classical phase transitions, the ones we are familiar with and everyone is familiar with. So in particular, here I show you the phase diagram of water as a function of temperature and pressure. We are very familiar with this. So for high temperatures, we are in the fluid phase. That can be either the gas or the liquid. But as we lower the temperature, then we can go through a phase transition to a solid regime that we call ice in different forms and so on. Okay? But this idea that is extremely simple or extremely natural for us, that we have around these kind of phase transitions in our daily lives, so we are used to it. I want to raise one question about it. I don't know if you have thought about it, but it's kind of the main thing to understand what can be quantum and not. How does water know when to change phase? Okay? So imagine that I have it in the solid form, okay? So I am down in the diagram, and then suddenly, without, it's not adiabatic, nothing. I just change the temperature from solid to fluid. Okay, how does water know that it has to change? Anyone? You are free to answer. There are no wrong questions. So, yeah?
The energy of the bonds? Related to the energy of the bonds?
Maybe. Yeah, it's not a bad idea. Then one more, if you want. If not, I tell you the answer. It's actually very simple once they tell you. Yeah? Thermal fluctuations, that's the idea. So water doesn't know anything. Water is just a bunch of atoms, molecules, whatever, that are all the time moving because of thermal fluctuations. So when they are in the solid phase, they are moving. Very, very tiny motion, whatever you want, but they are moving, so they are exploring other phases all the time. So they are trying to get out, but they don't want because they are comfortable there. It's the state, the equilibrium thermal state that minimizes, let's say, the energy in the simplest form. And you all know our thermodynamical variables and so on. But the point is that because we have thermal fluctuations, when we suddenly change the temperature higher, then the molecules which are bouncing around, they suddenly see a landscape of energies that are lower. They say, oh, staying here actually cost me more energy than actually flying away, going somewhere, doing something else, okay? So it's because even though we see a solid that it looks pretty much stationary, steady, but it's because in reality, the solid is all the time moving around because of thermal fluctuations. That's what creates the possibility of flying out of one phase into another, okay? So we say that thermal fluctuations drive the phase change, okay? But then, of course, naturally, then people before quantum mechanics, they were saying, okay, this means that at 0 temperature, if we don't have temperature, so if we really lower the temperature to 0, there are no thermal fluctuations, things are completely stationary, there cannot be phase transitions, okay? There are no phase transitions in classical physics, let's say, at 0 temperature. And you can see it in this diagram, for example. So you go to the 0 temperature line, you start moving in pressure, for example, and you don't see any phase change. You are in the solid phase, and you remain in the solid phase. But once quantum mechanics entered into the game, then it became very exciting also for statistical physics and this field of phase transitions. Because even at 0 temperature, we know that there are quantum fluctuations. And those are natural fluctuations that we cannot get rid of. Okay, so every system, for example, your beloved harmonic oscillator, it's always exploring in position and momentum uncertainties, right? It has the uncertainties. You can lower the uncertainties of one, but then you increment the uncertainty on the other. So it's always flying around of, let's say, the equilibrium position. So then quantum fluctuations can also drive phase transitions, not only thermal fluctuations, okay? And in particular for low temperatures, in particular for 0 temperature, quantum fluctuations are the driving mechanism for phase changes. Or in other words, this means that quantum fluctuations can induce phase changes, but because these fluctuations are quantum, and then they have the possibility of being, for example, of creating quantum superpositions, we might access new phases of matter that were not available with thermal classical fluctuations, okay? So then quantum fluctuations can drive the system through phase transitions into phases that exploit the quantum mechanical properties, strange properties that we all love, okay, to create new phases of matter that were not there before, okay? So if you get away anything from this talk, I hope it's this idea of what quantum phase transitions are, okay? And I give you just a bunch of quantum phase transitions or quantum phases of matter induced by phase transitions driven by quantum fluctuations. And you know all the names probably by now, but most of the names for sure. Superfluids and superconductors are the first ones that were observed in the 70s. But then later on, we had predictions and experiments observing things like supersolids that I don't have time to talk about. Time crystals appeared very recently, let's say, that in the last 15 years or so. And today we will talk mainly about these kind of time crystals. But let me, before, just show you one model, which is not a surprise, is the Bose-Hubbard model, that has a quantum phase transition. And let me show you the phase diagram for this model, just as an example of a quantum system that has this kind of transition. So this is the phase diagram of the Bose-Hubbard model at what we call unit filling. This means that on every lattice site, you put one atom, okay? So the density is one atom per site. And now you can change in this model, let's say, the ratio. So only in the Hamiltonian, only one parameter, which is the ratio between the interactions and the hopping or quantum tunneling, okay? That's what we have in the horizontal axis. And in the vertical axis, we can have the temperature, okay? So the phase diagram looks like this. So when the temperature is very high, essentially, the system behaves like a normal fluid. So the particles can go from one place to another, just like in a normal fluid. But when you lower the temperature, then you see that actually you have two different types of behavior. One is insulator. That means that if you put one excitation in one side, that won't travel, okay? That won't conduct, if you want, okay? It won't go from one place to another. It will remain localized, okay? And the other one is superfluid, which is the opposite, right? You put an excitation in one place, and it starts flowing into other sites. But the interesting thing here is what I was telling you before, that at zero temperature, if you go to really the horizontal line below, you see that you have a phase transition between superfluid and insulator, okay? And that kind of behavior can only happen because the fluctuations that are driving the phase transition are quantum, okay? Quantum fluctuations and not thermal fluctuations. So of course, as you raise the temperature, there is a competition between these two types of fluctuations, and at some point, all the quantum properties are broken, let's say, because thermal fluctuations dominate, okay? So this is just an example of a model that has this kind of phase transition, but as I say, this field of quantum phase transition is a huge field in condensed matter and many body physics and so on, since many, many decades ago. And I find it very interesting. Okay, but like I said, now we will focus for the rest of the talk in one particular phase that is called time crystals. And I will be introducing what time crystals are and, let's say, what we have done in our group in this field of time crystals. So with this, if you want, we can take a break, and I leave this slide prepared. And yeah, I think it's a good time to do a break, maybe 10 or 15 minutes, I don't know. Maybe 10 minutes, I think it's fine. And then I tell you the story about time crystals. So we regroup at 9:55.
Well,
if anyone has a question, like you can ask in the middle of the talk, because this was very blah, blah, blah. I think it was fine, but in the next part that will be more technical, please stop me, ask anything. It's okay if we don't reach the end. Okay, I prefer that we do only a couple of things. Yeah.
I had a question.
Can I throw you this?
Yeah. You want? Hola. So I had a question. I'm not really sure exactly the details of my question, how the definitions are going to be, so please correct me on that as well.
Yeah.
But in between two quantum phase transitions, so the point in between them,
Yeah.
Doesn't something funky happen, like chaotic system or some symmetry breaking in between?
Yeah. I mean, so anything that happens in the world of phase transitions can happen in quantum phase transitions. So that point that connects two different phases is what we call a non-analytical point. So something funky has to happen in there. And it can be anything, okay, if you think about it. So of course, many phases are classified by the symmetries they break spontaneously. And then you can have the mechanism of spontaneous symmetry breaking, like one phase that was symmetry preserving, then when you go through that point, then suddenly the system breaks spontaneously that symmetry, and that comes with a lot of physics. You know some of the physics. You have heard all about Goldstone modes because you all have heard about the Higgs boson, for example, which is one of these type of particles, one of these kind of phenomena. But many other things happen, like the slowdown of dynamics. Like when you are close to a critical point, the dynamics slow down a lot. And a lot of things can happen, including chaos, including many things, yes. Yeah.
And what did, in the Keeble Zurek, didn't Zurek do something with quantum phase transitions?
Yeah, 100%. Like the Keeble Zurek mechanism tells you exactly how these fluctuations grow, let's say, to generate from one phase another phase. I'm not an expert in the Keeble Zurek mechanism, but essentially this is a thing that is completely related to what happens when you cross the phase transition. When you have a fluctuation that suddenly you drive through the transition, and how fast you can go, and all these kind of things appear in this thing. Yeah, but these are good keywords that if you want, you can follow. Yeah.
Thank you so much.
Okay.
Someone has a question?
Yeah. I was wondering in the last slide where you showed the phase diagram for the
Yeah.
How would you include temperature in the model? So the Hamiltonian is at 0 temperature?
Yeah, I mean, you are talking about equilibrium states. So in equilibrium physics, you always include temperature in the same way. You just assume that the system is in the Gibbs state, exponential of minus h divided kt, t being the temperature and k the Boltzmann constant. Okay, so you have that state, and then that state has the parameters of the Hamiltonian plus the temperature. Okay, that's how you do it. Yeah, technically in a computer, how you would do it, maybe it's in a different way. You can run imaginary time dynamics, which is equivalent to lowering the temperature or putting the temperature higher. So there are technicisms. But the point is that essentially what you're saying is my system is in a Gibbs state at equilibrium exponential of minus h divided kt. Okay, that would be in the canonical ensemble. If you have other ensembles like the grand canonical ensemble, you add the restrictions of the grand canonical ensemble or whatever. But the point is that temperature appears in the state, not in the Hamiltonian. Yeah.
I see. Thanks.
Okay. Yeah.
Throw the...
We have another one, but yeah.
Hello. Thank you for the presentation. It's for me very you explained very clear.
Thank you.
Yeah, sure. When you show the circuit of Josephson-Johnson, you connect in serial many blocks of Josephson-Johnson, and I'm very curious about what is the input, how you excite the circuit, and what is the idea to obtain and connect with the theoretical quantum fluctuation.
Yeah, I mean, there are many ways to do these kind of things. Like in here, to be honest, the only reason why I put these two Josephson junctions in parallel is because they look pretty. Okay, you could just change the inductor by one Josephson junction, and it would also create a nonlinearity. These two junctions in parallel are very interesting also for one reason. I mean, it's the one I use when I do theoretical models, these parallel junctions, because the magnetic, let's say that this makes the system sensitive to the magnetic fields that go through the junctions, because the flux, the magnetic flux in this, essentially this closed circuit essentially changes the physics of what's going on in there, right? So then you can use an external magnetic field to drive the system, for example, okay? So you can couple your circuit to an external magnetic field that you can modify at will. Okay? But if you want, you can also just do something much simpler, which is take the cables that you have in there, the superconducting cables, okay? But allow me the language, okay? You can take the cables, you can just put a capacitor and connect it to a transmission line. That transmission line can be as large as you want. It's an environment like the output of a cavity, an optical cavity. So it's the same. You have a transmission line. And now in that transmission line, the end could be a generator of signals that you can drive the circuit with. But of course, that creates also dissipation. And then you can monitor the system through that transmission line and so on. Okay? So essentially, there are many ways of interconnecting both the circuits and the circuits to the external fields that you use to drive them, okay? There are many, many ways. And I use some of them to do physics beyond what you can do in condensed matter. But yeah, I didn't prepare a slide for the type of processes, but we can talk if you are curious about it.
Okay, thank you.
Yeah.
Okay. If there are no more questions, I think we can meet the break. A 10-minute break, okay?
Yeah, so maybe we will regroup at 10,
At 10.
if you want. Then we have half an hour for time crystals. Okay, thank you.
se van a mandar a los que hemos asistido a estas presentaciones.
Okay, so let's continue with the talk.
Okay, so thank you all for staying for the second part. So like I promised, so right now I will be telling you about time crystalline phases of matter, in particular in the context of open quantum systems. The talk could be 1 hour long, so don't worry about time. I will just stop at 10:30, wherever we are, and hopefully at least you will get the idea of what time crystalline phase of matter is and how it appears in open systems. And then the main results of our projects, you can discuss them later with me or with my students or whatever. Okay. So first of all, let me just tell you the people who have been involved in the ideas that I am going to talk about, because this started long ago. This dates way back, actually, to my PhD times, before even the time crystals appear, okay? All these things about time and time symmetry. I already dealt with them in my PhD. But the things I am going to talk about started in Germany. Sorry, the 3 pictures there, continued in Shanghai, in here, and now in Valencia, we are developing these ideas with Evi and with Jorge, who, as I said, are here. And Jorge will be talking about some of the things, extending some of the things I will be telling here. Okay, so first of all, probably the first idea I have to introduce is what's a time crystal, okay? What are time crystals? And for that, let me first take a step back and talk about what are crystals, like spatial crystals, the crystals we are used to. So for that, let's consider a bunch of particles, okay, that are confined to a volume, okay? They have to stay in some volume. And then these particles, of course, can have kinetic energy. They can move around, and they can have repulsion. So they can have interactions in the form of repulsion, for example. So when the temperature is very high, we all know that the particles, basically the repulsion doesn't play a big role. The particles have a lot of kinetic energy and are just flying around. They don't even have time to see each other to interact, okay? But as we lower the temperature, it can happen that the kinetic energy starts going down, 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 and at some point, the repulsion takes over, and the particles self-organize. So they want to stay, let's say, as apart as possible in the volume, okay? And then you end up with what we call a crystalline structure, so with an organized and ordered structure that essentially can look something like that. But there is something very deep about what happened in here that maybe you are not thinking about, and I want to explain you, which is the following. The system itself, the original system, is invariant under under translations in space, okay? So of course, the kinetic energy of the particles is the same if I have them here or I have them here, okay? And the interaction between the particles, it remains the same if I have the particles here or I move all of them at the same time to here. Okay, that's a symmetry of whatever you want to call it, the Hamiltonian, the equations of motion, the dynamics, okay? And it's also a symmetry of the state for high temperatures because the system is disorganized. So if I look with a microscope in there, no matter where I look, I will observe exactly the same, okay? Essentially an average of particles, which is the same everywhere. But when the particles self-organize, something very deep happens, which is what we call spontaneous translational symmetry breaking. Because now, even though the equations of motion, the system, is invariant under translations, the state of the particles is not, okay? Because now if I look with a microscope, it's not the same. If I look where I have a particle, I see a particle, but if I look in another place, I don't have a particle, okay? So the density is not invariant under translations in space. And you can see that because if I just move, okay, you can see that now we can see the state in the background that was there before, okay? So this is essentially the main property of a crystal, spontaneous translational symmetry breaking, okay? Of course, in order for it to be a crystal, this symmetry breaking has to leave a residual symmetry, which now is discrete. So I can do a translation by the, let's say, the lattice constant, right? And the system will not change. I mean, but it's not continuous translations anymore. Now it's only discrete translations. I have to really move all the atoms one side to the left, one side to the right, whatever I want, but discretely. And more importantly, or equally important, is not only that I have spontaneous translational symmetry breaking, but that this state that breaks the symmetry is robust against local fluctuations. So that means that if I have my particles organized, the crystal doesn't break because I just touch a little bit one particle and then everything melts, okay? It has to be robust against, for example, thermal fluctuations that we were talking about. And of course, even quantum fluctuations, okay? If the crystal is not robust against fluctuations, in particular local fluctuations, then we cannot consider it a crystal. I mean, it will be an organized structure of some sort that it's very sensitive or very fragile, and it can still be interesting, but it's not a crystal. What else I wanted to say about this? Yeah, something went out of my mind, but probably I will be able to pick it up later. Okay. So how about time crystals? So essentially, in physics, since very long ago, more than 100 years ago, we have kind of this equality in a way, or similarity between space and time. So then at some point, it took a very long time, okay? But someone said, okay, if we can have this spontaneous translational symmetry breaking in space, can we have it in time? So could we have a system of particles or whatever, a system that the equations of motion are invariant under time translations. So that means that there is no explicit time dependence of anything, but let's say the state that the system evolves into or wants to stay at, the equilibrium state if you want, is doing something like oscillations, okay, in a robust way. So this was the idea that in 2012, Frank Wilczek introduced. And the paper of Frank is basically can be summarized in why not, okay? It's a paper that simply says, hey, we have this. No one has said it explicitly. Let me say it explicitly. Maybe we could have this kind of thing. Why not? Let me give you a model. And I think this model satisfies this thing that I am talking about. The ground state oscillates, if you want, okay? So I know it's a step to call an oscillating thing a ground state, because ground states usually are states that are fixed. But let's say that the equilibrium state, the state that minimizes the thermodynamic variables, the energy, whatever, it's a state of oscillation, of continuous oscillation, okay? So why not? He gave a model, then the model was criticized later, in particular in 2015. Some people claim that they have proven that at equilibrium this is impossible, okay? Then some people proved that this proof was not completely clear, and in particular, it assumed certain things that you can use to get away out of the no-go theorem, let's say. But the point is that at equilibrium, it's kind of unclear what are the conditions or whether it is possible to actually have a system of particles, let's say, that at equilibrium, they naturally, spontaneously start oscillating. Also, this sounds a bit like the eternal engine, how do you call it? The perpetual motion machine, right? It's a little bit weird. So then lately, the attention has shifted to non-equilibrium situations that we study in quantum optics, okay? And in particular in here, I will be talking about this concept of time crystals in driven dissipative or open systems in general, okay? And then from here on, because, well, I know that you are all an audience of people who know a lot about quantum mechanics and probably open systems. You have gone through masters in quantum mechanics and quantum technologies and so on. So from here on, everything is going to be a bit more technical or quite more technical. Still, I hope very understandable, but I want you to really get the idea of what are open systems and how to use them to create time crystals and so on, okay? So I thought that from now on, it was good for you, and it was respect from me to you to actually show you how it's done technically. So let me start by reminding you, hopefully, most of you, and if some of you don't know about it, hopefully make you understand a little bit about the theory of open quantum systems. So essentially, an open quantum system, you have it there. It's essentially a system that instead of just closed, described with dynamics described by a Hamiltonian, it's a system that can interact with an environment, okay? This environment can be something very large, which is, let's say, the situation that I usually have in mind and that most people have in mind. We have a huge environment with infinite degrees of freedom, and then we have a tiny system interacting with it, okay? Then the dynamics of the open system can no longer be described just by, let's say, a Hamiltonian evolution, but you need to take into account the interaction with the environment. And if you, let's say, integrate out the environment formally, then you are left with equation of motion for the open system, which is not the Schrödinger equation anymore, and I will be talking a little bit about this now, okay? But the most important thing to get first is that once you have an open system, because information can leak out of the system into the environment, you no longer are dealing with pure states. Okay? You cannot tell anymore if the system is in one pure state or in another, because maybe that's entangled with the environment. And when you trace out the environment, then you are left with a mixed state. So then, in open quantum systems, the natural state of the system is a mixed state, what we call a density operator. So in quantum mechanics of open systems, essentially, the most general state that you can have at any time is an operator which is Hermitian, it's positive, so it has positive eigenvalues or 0, and it's normalized. Okay, it's normalizable. So we normalize it to 1, trace 1. So probably you know this, but just to set things straight. So also I will be using this from time to time, but expectation values in quantum mechanics that you know, when you are dealing with a mixed state, you calculate them in this way. It's the trace of the state times the operator. Okay? These are just definitions that I think you all know. But what's more interesting for me, and what will be the key to all this time crystal business, is the dynamics. Okay? So how do we describe the dynamics of open systems? In general, it's a mess. It's very complicated because, of course, the whole system plus environment, universe, if you want to call it like that, evolves according to an interaction Hamiltonian and so on. So everything, it's a Hamiltonian. But when you reduce the dynamics to only the system, then lots of different regimes appear in which you have to describe the dynamics of the system through different equations. So here I am going to focus on the simplest scenario, what we call the Markovian and divisible scenario. Markovianity, I think you all know what it means. It essentially means that the state at a later differentially connected time, okay, in the next differential step, depends only on the previous step. Okay? It doesn't have memory. Okay? That happens very naturally for many environments and system types of interaction. And divisible, maybe it's something that you don't remember, but you know it very well. Divisibility is something extremely simple. It's just that so the map that gives you the evolution from time t1 to t2 is the same as the map going from t1 to an intermediate time and then from t2 to the final time. Okay? That we call divisibility. So you can always take the evolution, and instead of directly going from one time to another, you go in steps to the next one. So when you consider these two approximations, and as I said, for open systems, these are approximations that appear very naturally in many contexts. I don't have time to go through exactly which context. You end up with, let's say, the canonical way of describing open systems, which is through something that you might know as the Lindblad master equation. The Lindblad master equation is this equation here. Okay? So all Markovian divisible, let's say, open systems obey an equation of this type. This is kind of the Schrödinger equation of open systems, okay? So if you want, you can identify in here actually the Schrödinger equation. So you have the commutator between the Hamiltonian and the state. That's the normal Hamiltonian evolution. The only maybe difference is that in this Hamiltonian, maybe you have to incorporate Hamiltonian parts generated by the environment, okay? But if there would be no environment, you will have a Hamiltonian of the system, and that would be the equation, and that's it. But whenever you have an environment, you also need to put the second term in the sum, okay, which are processes that we call incoherent processes, and I will explain you in a second. I will give you an intuition of all this in a second, that have this funny shape, okay? So essentially, you have a sum over processes. You can have many processes, depends on what the environment is doing. Maybe it's dissipating, maybe it's giving energy, maybe it's creating dephasing. We will talk about a few of these, okay? So for every process, you have one of these D terms, okay? These incoherent terms. And the form of these incoherent terms is quite funny because you can see that the second, so this part in here, it's an anti-commutator. Okay? It's kind of like the commutator that we have in the Schrödinger equation, but in this case, it's an anti-commutator. But then we have this second part in here, or this first part in here, which is something new, let's say, that it has nothing to do with the structure that we had in quantum physics of closed systems. And before proceeding, so I want to actually get an intuition of what this master equation, well, we call it Lindblad master equation, is doing, okay? And for this, I won't do a proof of the following, but you have it in my lecture notes. I forgot to advertise them here, but if you want, I can give you the reference later. But for this, I will show you, or I will explain you better, that this equation, this evolution equation, is exactly equivalent to the following stochastic process, okay? It's a very simple stochastic process. This means random process, essentially, which is the following. With some probability, in particular this probability here, okay? Since I have it here, I can point with the finger. So with some probability, we apply the process M, and I will explain exactly what. So the probability, take a look at the units if you want. This is a rate, and this is time. So this is unitless, and then you have the expectation value of kind of the positive operator generated from these J operators for each process. These J operators are called quantum jump operators, and it's for a reason, because what I say is that this stochastic process is, with some probability, I apply a quantum jump. So the state at a later time, okay, it's the previous state where I suddenly apply the jump operators, okay? If this would be a pure state, what I am saying is I just take the operator J, the jump operator J, and I apply it like that. It's not differential, it's not anything. It's just application of the jump operator onto the vector. That's it. That we call it quantum jump. And it's very important that you understand that that's irreversible evolution. That's not reversible evolution, because the jump operators in general are not invertible. So this means that if you have a quantum jump in the system, if you have this process in the system, you cannot, in the lab, be monitoring it and then suddenly undo it. So apply the inverse operation to go back to the state that you were. Okay, because there is no inverse operation. Okay, maybe you can think of if the jump operator would be the annihilation operator of a harmonic oscillator, that would mean that you are removing excitations. So you remove an excitation onto the system, but remember that the annihilation operator is not invertible. There is no A minus 1, okay? That doesn't exist. So then essentially, you have, with some probability, you create an irreversible quantum jump. And then with the leftover probability, which actually is the larger one typically, you create reversible evolution according to an effective Hamiltonian, which contains both the Hamiltonian and some imaginary part in the Hamiltonian, okay? So you just define the unitary evolution operator, which is the exponential of this times t, okay, times dt in this case. And that generates the evolution to the next step, okay? But that's invertible, because I can always create the exponential of minus the Hamiltonian times dt divided by h bar. So then we have part of the evolution with some probability happens an evolution that is reversible, and with some probability happens something that is irreversible, okay? And that's how you have to read a master equation. Every time you see a master equation like this, you always have to say, okay, I look at here, and I see the quantum jump processes, irreversible processes that I might have, okay? And that's what we will do when I show you models, okay? We see which particular quantum jumps can happen in the system. And then we will have a Hamiltonian, and then the other part of the master equation is just reversible, okay? But this is something interesting, and I could be talking about this for ages, related also to classical descriptions and so on, but I hope that all of you are kind of familiar with this. And please stop me if you have any questions, because this will be more like a lecture from now on. So if you want, I can tell you about, yeah.
I'm wondering about the reversibility of this effective Hamiltonian, because of course it's non-Hermitian, so
yes.
the reverse dynamic would be you gain some norm.
Yes. But I mean, this is not something weird in classical physics either, because when you have an imaginary part in your Hamiltonian, that usually means that you have dissipation or that you have some kind of pumping mechanism, something like that. That's not the point. Is that mathematically you can always revert the operator, the exponential of this effective Hamiltonian. You can always change the sign, and then you go back to where you were. Okay. So in that sense, it's more theoretical. It's not like in the lab. I'm not saying it's easy in the lab to undo the evolution. I mean, it can be impossible or a mess, like technically. But mathematically, it's possible. So then it's reversible in spirit. Okay. Okay. But okay, no matter what interpretation, the point is that this master equation, it's essentially a linear operator, or the generator of the dynamics. It's a linear operator. We call it super operator because it acts on operators, on states. So it's an operator in the space of states of the system. We call it Liouvillean to that generator of the dynamics. Okay, and the point is that it's linear. That's important, because if it is linear, it means that no matter how complicated this equation is, it's like the Schrödinger equation in the sense that the evolution will just be exponential. Okay, you will just have the eigenvalues of the Liouvillean, the spectrum of the Liouvillean, and then the state at all times will be just the exponential of the eigenvalues times t multiplied by some operators in this case, which are connected to the eigen operators of the Liouvillean, whatever. But the important part is that you have exponential evolution according to the Liouvillean spectrum. And moreover, if the system has to be physical, think about what happens typically in an open system. So if you have a large environment and you have a small system, essentially what happens is that the environment starts doing things on the system, and then the reversible and irreversible dynamics eventually start compensating into some steady state or some asymptotic state that is the stable state to which the system arrives. Okay? So any open system is expected to reach some kind of asymptotic state, okay, that will be, let's say, in principle, independent on the initial state. It will just relax to some state. If you think about thermalization, it's exactly that. So you have a system, you want to thermalize it at some temperature, you put an environment at that temperature, and then the environment drives the system into the thermal state, things like this, okay? So but that mathematically means that these eigenvalues need to have a real part, that is negative. Because if the eigenvalues would have a positive part, the state would just exponentially explode up, up, up. But if they are negative, all the negative eigenvalues will essentially be canceled or be canceling with the exponentials, the operator Cn, except for at least one that has to be zero or have a zero real part, that will be the steady state. So this will give you the actual steady state of the system, okay? So this is essentially the setting that we have in open systems, in Markovian open systems. And is what I will use to introduce to you time crystals. I see that we are almost on time, so I will just introduce time crystals. And if you want models that are time crystals, I will give them to you later, or I can explain you. Or you can go to the poster of Jorge. Also, you can talk to Evie, and she knows about this as well. OK, so in this context, what is a time crystal, what we call dissipative time crystals? So after what I have explained you, I can actually give you a definition that is not mathematical at all, which is this. So we will say that an open system is in a time crystalline phase, okay, if without any external periodic forcing, that sounds very mathematical if you want, but essentially it means that the master equation is time independent. So there is no explicit time dependency. That means that the system is invariant under time translations. We are not giving a clock to the system. We are not giving any information about time to the system. So without any external periodic forcing, it relaxes to a state in which observable quantities oscillate, okay? And not only oscillate, but they oscillate in a robust fashion, okay? Like what I was talking about in a normal crystal. So let me go back to the master equation and explain you quickly how this can happen, because in principle, everyone who works in open systems is more used to the fact that the system reaches a steady state. So how can an open system oscillate? So how are these two views of the quantum open systems, how are they connected? Well, like I was saying, the Liouvillean spectrum needs to have a real part that is negative or 0, but this still allows, okay, this still allows for the spectrum to have eigenvalues that are purely imaginary, okay? So for example, if we would have plus minus I omega, okay, with omega some frequency, or any of the higher harmonics, or even the 0 eigenvalue, so if we would have any of these, let's say that it exists this part of the spectrum of the Liouvillean, then for t going to infinity, these ones would not dampen, right? Like the exponential would not fall to 0. So they will remain in here. And of course, this state, because you have these complex exponentials, is periodic in time, okay? So in particular, if you evaluate observable quantities, like I told you with the trace of rho acting on the operator, then you end up with an observable quantity that it's actually periodic, okay? It's equal if you shift the time by 2 pi divided by omega. So all you need in open systems, all you need, because it's not so easy to get as we would discuss if we will have time, but all you need in open systems to have a time crystal, it's finding a Liouvillean, so it's finding a master equation that has a spectrum with imaginary eigenvalues, okay? And then, of course, you have to check if it's robust against local perturbations or things like this, okay? So since I want to stop in here because I don't want to delay the conference, I will essentially leave you with this definition of time crystals. And like I said, essentially, we work in our group with models based on harmonic oscillators or models based on spins, okay? And if you have curiosity about the kind of models that can have this behavior and which ones are robust and which ones are not robust and things like this, we can talk. I mean, you can talk to me or to Jorge and David, who will be around more than me probably. Yeah. Okay, so with this, I think I will skip. I will give you an overview of the million slides that I have left. And you can start asking questions if you want, maybe for 5 minutes, even if we are a bit, yeah. I've never done this. I like it. Kind of, you know, it's animation in the questions.
Okay.
Yeah.
I think we have time for quick questions.
Thank you so much for the very educational talk. It was very nice. So perhaps you were about to explain this now.
Yeah.
And maybe you get this question all the time. So about time crystals.
Yeah.
So then, according to your definition,
yes.
What's the difference between a time crystal and a classical stable limit cycle solution of a nonlinear system?
That's exactly the first question we answer in this kind of work. There is a comment that I posted like 1 or 2 years ago in Archive that addresses this, because actually I was working with quantum properties of limit cycles for all my research life. So then I wonder when this field appeared, like, okay, what is the difference? Like, I think I have been working with time crystals my whole life and I didn't know. Yeah, okay, but it's actually very different, and that's the point. So a limit cycle can be just a single oscillator, for example, that starts oscillating. So typically, limit cycles appear in small systems, okay? But actually, most limit cycles are not robust against some kinds of perturbations or fluctuations, in particular, dephasing. So if you add dephasing on the system, you destroy any, let's say, limit cycle, classical limit cycle. When you put quantum mechanics and in particular dephasing, you destroy the oscillations, okay? It no longer oscillates in a robust fashion, and in particular in the steady state, the oscillations are canceled. So that would be the first thing. Of course, if the limit cycle appears in a big system, okay, let's say, each part of the system oscillates, let's say, synchronized in some way, maybe that limit cycle, even when you add fluctuations and quantum mechanics and everything, maybe that's still oscillating robustly, okay? And then it will be a time crystal. So the message is some limit cycles in extended systems or in many-body systems can be time crystals. But what we have found is that, let's say, every small system that oscillates will be destroyed by dephasing or other type of processes, okay? And it's about robustness. That's the main point. So let's say that if you want, I like to say that limit cycles are fragile time crystals. So if you are okay with fragility, then you can use them as a toy model or whatever. But of course, in the lab, I wouldn't use them as time crystals to implement my quantum computer or whatever.
Can I ask a quick follow-up?
Yeah.
Very, very super quick follow-up. So then this means that if I have a quantum system like yours, and I now apply the mean field approximation, and I find, and maybe I have a large many modes and so on, and I find some limit cycle solution, and I found that it's stable, meaning that by definition it will be robust against small perturbations. The Bogoliubov modes will be stable around the solution. Then you say that this might still not be a time crystal because if I have dephasing, still I'm able to destroy it, and this is something that will go outside of this mean field stability.
Exactly.
Okay.
Yeah. You have to use stochastic physics because dephasing means that you have some kind of noise acting on the phase of the system, and that's very tricky. Yeah.
Thanks.
You cannot use mean field for that.
Okay, so well, I think for the second of time we have to end
you
here.
Can ask me later.
You can ask him in the coffee break.
Someone is watching online.
There is people online. I didn't know. Yeah. Hello world. Sorry, I moved so much. I hope you saw me.
So. Okay, ask.
So they asked, does irreversible process decohere the quantum system?
And not necessarily. That depends on what is the actual irreversible process. So imagine that the irreversible process is made up of a sum of annihilation operators or creation operators. So then, of different harmonic oscillators. So then the generation of excitations creates in parallel in both modes, and then you are creating coherence. So for some engineered dissipation, we can create coherence through dissipation. Okay? This is something well known, and that has been implemented in the lab. But let's say that the question is not, going in the wrong direction, because in general, like if you don't do anything to your environment and so on, then most likely all the dissipative processes will create, or irreversible processes will create quantum jumps that destroy coherence, okay? But it's not mathematically necessarily, okay? It's not like that. So you can create coherence also through quantum jumps.
Okay, so let's thank the speaker again.
Thank you.
Let's go. But, here we go now. Batman scoop on the mic, mix in the mix on the wheels of steel. This is what I was fucking born to do. Yes, let's go.
Hello. Welcome to the contributed talks. The first speaker is Emre Kose from the Institut de Física Corpuscular de la Universidad de Valencia.
Hello, everyone. Thank you very much for the organizers for this event, and then let me to speak this talk that is going to be about multi-encoded quantum parameter estimation. Maybe I can just give a brief motivation why actually we are interested in mode-encoded parameters, and then what do they represent, and then what are the recent somehow progress. We can start with this simple, actually, model that we have 2-point sources. Actually, this is a very old model, maybe more than 100 years old, that, okay, if you want to resolve these 2-point sources, once the source separation goes to 0, in the image plane, you perform an intensity measurement, and then you will see that you cannot actually resolve after some point. And then this is known as a Rayleigh curse of these resolving the images. But in 2016, there was this theoretician, Mankai Tsang, and he showed that, okay, there is something wrong with this model. That's actually nothing wrong, but there is some problems that in our measurement that we are performing in the image plane. And that actually, the problem is, okay, we are just making an intensity measurement, and then that's not the correct measurement. How actually he got this idea is he calculated some elements that we are using for the quantum metrology, and one of them is we say quantum Cramer bound and quantum Fisher information. Once you calculate the quantum Fisher information for this problem, you will see that, okay, once the source separation goes to 0, and quantum Fisher information actually goes to a constant, which means that for your estimator, there is a hope that you can actually saturate this bound with the correct measurements. Then later, they analyzed the correct measurements, and then they found out that, okay, if you perform a measurement in the Hermite Gaussian basis, that you can actually really resolve these 2-point sources so that there is no Rayleigh curse. So it's fascinating that they discovered this really like 10 years ago. Then after that, okay, there is a growing community of imaging that's, okay, what else we can do? Since these are originally two incoherent sources, and then everything actually stays still in the standard quantum limit. So everything scales with the mean photon number linearly. But can we do something more? And at that point, actually, we asked the question, okay, what if I engineer these 2-point sources such a way that I can get something like a Heisenberg quadratic type of scaling or sub-Heisenberg scaling? And for this one, actually, we need to create the model from the scratch. Okay, what are we thinking of? Okay, we have this mode basis, and then we have the state, and then we have this generator. Means that, okay, I have the system, some modes that I can access to, and I have the environment, some modes that I cannot access to. And there is also an interaction between them. And from that one, I will show the way to calculate the quantum Fisher information. And then we will see that this actual quantum Fisher information is very nice, and then splits into 2 parts. And then this is general for any linear optics, passive linear optics regime. And also, you can check this paper, which is published by Manuel here. And OK, let's start. Now we have this common field mode, which doesn't contain any parameter. And what we do is that, OK, we have this function, which contains the parameter, and then we encode the parameter onto these modes. So what we are doing is, OK, in the end, we have these system modes and then the environment modes with this G function, which encodes the parameter to the environment. And those modes, in the end, E and A is going to contain the parameter. So in the end, yes, we have this mode basis. In the end, contains the parameter. If there is such a transformation, this is passive linear optic transformation, that I can actually write a unitary which acts on some mode basis, which doesn't contain the parameter, and then which gives me the mode space which contains the parameter. So it's the situation is something like this, that, OK, you have this somehow complete basis, which contains all the modes that you are interested in, and also the modes that you cannot measure, maybe. And then you encode the parameter, and then this actually deforms your mode space. Now here, we can define some quantities, like this Q. And then this Q here, that, OK, you can, because you are calculating the quantum Fisher information, what you are looking for is the derivative of this unitary, and then how actually it changes your quantum states. And then you can define this anti-Hermitian operator. And now from this one, you can define a generator, actually, that actually encodes the parameter to your quantum state. So which is nice, but then we can write this generator into different forms. Like, OK, you have this system modes that you can access to, and then you have the environment you cannot access to, and then you have the interaction between them. And the most important part is the elements of these functions, actually, this operator is here f prime means that, okay, derivative with respect to the mode functions, and then their overlaps within the environment, within the system, and then with the interaction term with the environment and the system. Because once you take the derivative actually, this mode function doesn't actually live directly in your mode space. It lives in between the mode space that you have access to and the environment modes. So if you can access everything, then we know the result of the quantum Fisher information, which is the 4 times the variance of this total generator, whatever it is. And we know that for the accessible system, if we cannot access all the modes, that this is actually upper bounded by this total quantum Fisher information. Now, but the goal is to calculate really this reduced state quantum Fisher information so that we can understand how far from actually, with our measurements, that how far away from this bound. So good. So what we are going to do now, we have this open type of systems that I can generate any state for these accessible modes, the blue ones. And then the red ones are the ones that actually are inaccessible. Initially, I can assume that they are in the vacuum. So that actually this is a nice approximation, especially in the optical domain, that you can assume that, okay, they are in the vacuum state, the initial environment modes. And the process is that, okay, you can show it with the Krauss operators, that because you need to trace out these inaccessible modes. And then you actually measure your accessible modes. Now for this process, again, to calculate the quantum Fisher information, what you need to do, you need to calculate the derivative of this quantum state. And then the derivative of this quantum state becomes like this. Actually, this is, you may think that, okay, this is like a Limblad type of equation. But right now, the derivative not with respect to the time, but with respect to the parameter that I am interested in. And, but this equation, normally what we do, if we can solve it, we just put into this SLD equation and then calculate the quantum Fisher information directly from this one. But since we have this huge Hilbert space, it is extremely difficult. What you need to do, you need to either cut the Hilbert space at some point with we reduce the size and then try to solve it numerically. But even that one is going to take a lot of time if you have more than some 30 modes, and if you need to cut the Hilbert space up to, I don't know, some 30 by 30 matrix. And, but what we can do, we can look at the local point, because we are looking at the quantum Fisher information, and then the quantum Fisher information is local, so that we can directly focus on some local points, and then give an explicit solution what we can do with this. Now, let's say that, okay, theta equals to 0. I can assume that my unitary is identity, but the Krauss operator, the derivative of the Krauss operators actually are not just 0, but since I'm looking at the point and then how actually this changes around the point, then the Krauss derivative gives me some term, which is actually the Hamiltonian within the system, and also other terms like these terms, which are like the jump operators. Now, once you have this Krauss operators, what you can do, you just go back and then just use the purification and minimization formula to calculate the quantum Fisher information. And in the end, you can just use the Krauss degrees of freedom to minimize everything, and then you will get quantum Fisher information for the reduced state at this local point. So this is a local quantum Fisher information. And then once you've done all these calculations, you see that, okay, this actually splits into very nice 2 parts. And the one part, which is very interesting, which is always within the accessible modes. And the condition is that if you have a Heisenberg type of scaling, what you want is that the derivative of the modes actually overlapping with, with your modes is going to survive. If this term doesn't survive, you can see that, yeah, okay, you will never have Heisenberg type of scaling. And then for the other part, this is the leakage part, which always in the standard quantum limit. And in the end, you will see that calculations in the end end up with, okay, you have this mean photon number, which scales always with n. And in the end, OK, this was the point at θ equals to 0, but you can make it quite general. You can immediately shift the point wherever you like, and then just write the general form of this one so that you can calculate the QFI. The main message is here that, OK, you can split into these two parts very nicely, and then those are closed form solutions that you can really find and calculate analytically. So in the end, we can compare that this leakage part and then this unitary part. And then unitary part, actually, the most advantageous part is that it can give Heisenberg scaling. And then this leakage part is always in the quantum, standard quantum scaling. But to survive, actually, this one, that you need to engineer your modes such a way that their overlap should survive. If it doesn't survive, that you will never have Heisenberg type of scaling. And here, OK, this is the general idea. Now, next talk, Balázs is going to give actually some examples, physical examples, that how we can apply to these common problems and then get Heisenberg type of scaling for these images. Yes. Thank you very much.
Thank you for your presentation. Is there any question? No? Well, I had a question about, well, Balázs is going to talk about that, but I was wondering, do you have any real-life implementation of this encoding?
Actually, anything that you can think of in the passive linear optical regime actually encodes a parameter that you are interested in. It can be either, in this case, like the source separation, or it can be even like a LIGO, that what you want is to understand the gravitational waves, and then you send a squeeze light, and then this is again the similar problem that what you want to do, you want to understand the shift on this squeeze light so that you can measure. So any kind of this passive linear Gaussian encoding is useful here that you can apply to pretty much anything. And the nice thing is here that your states, not necessarily just the incoherent states, but they can be some fancy states like null states or GKP states or whatever.
Okay.
That you can get some quantum advantage from.
Okay, thank you.
Welcome. Okay.
The next speaker is Balázs Novák, also from Institut de Física Corpuscular de la Universidad de Valencia.
Thank you. So that was part one. Now comes part two. Because my PhD project is applying this framework of mode parameter estimation to the specific problem of two-point source imaging that Emre has already alluded to. But just to give a rough sketch of what this looks like, we start with two incoherent point-like sources that emit photons. And these sources are separated by a distance s. And our task is to try and estimate this separation s. And there are some transformations that the photons undergo that are unavoidable. Firstly, they are going to interact with the environment, and there are going to be some losses. So we almost never able to measure all the photons that are emitted. We can model these with beam splitters that mixes the original modes with some environmental modes. Then we also have, because we assume a diffraction-limited imaging in the far field, when the photons go into the detector, they go through the aperture, and they're going to be diffracted. So what you see on the screen is not just two dots. On the image screen, you get two blobs. And these blobs are going to be described by what's called the point spread function. And this point spread function depends on the parameter s, this parameter that we try to estimate. So on the screen, the quantum state is described by a state where the parameter is encoded into the mode structure of the light, not into the quantum state itself. In fact, we assume that the quantum state itself does not depend on the parameter, only this point spread function. Now, a quick technical detail that I must mention is that because these two point spread functions overlap as s goes to 0, as the overlap goes to 0, these two operators, the A1s and A2s, that are the creation and annihilation operators of the quantum state on the image screen, these will not be orthogonal. So the first thing we do is we have to orthogonalize these states, and then we get these symmetric and antisymmetric operators that we have to work with. And what we're doing then is we fix a reference point. So most convenient is to set s equals 0, and we see how things change as the parameter fluctuates around this reference point. And this can be modeled as a beam splitter, and this will generate this effective Hamiltonian, which then can lead to this quantum enhancement, that n-squared scaling term in the quantum Fisher information that describes the sensitivity of our estimation. And this is what Emre has been talking about. So what we're looking for is this effective Hamiltonian. This depends on the overlap between the original modes, so these point-spread functions, and derivatives of these original modes. So if we have those, we can have this effective Hamiltonian, and then we have a hope for quantum enhancement. So it turns out that in this setup, we have two strategies to obtain this effective Hamiltonian. One is engineering the point-spread function, and the other one is populating additional auxiliary modes proportional to these derivative modes, because their derivative modes can have an overlap with the original modes. So then we still get this effective Hamiltonian. Now, point-spread function engineering, it's very important that we keep the point-spread function completely general, so we say that it can have a phase, and its phase can depend on the parameter in general. This is very important because in most experiments and most other work, it's usually said to be a constant, this phase. So the point-spread function is just a real, usually a Gaussian function. But what we find is that if you do that, this effective Hamiltonian just vanishes. Same for the quadratic phase, by the way. So this explains already why, when people previously tried to implement highly non-classical states in the initial state, they still were unable to obtain this Heisenberg scaling, this quantum enhancement. And that's because you need, unless you apply the second strategy as well, you do need a phase of the point-spread function that is not a constant. In fact, if you use a linear or a cubic phase, you do get an effective Hamiltonian. So with the second strategy, if you populate some additional auxiliary modes, even with a constant phase point-spread function, you can get an effective Hamiltonian. So that you can diagonalize nicely, and you immediately get a nice optimal state and the desired n-squared scaling in the quantum Fisher information. So you get a sensitivity that scales better than what you would be able to obtain with any classical method. But this is ignoring the environment. And I will talk about the environment in a second, how it affects the whole story. But first, I want to talk about the linear phase point-spread function and that strategy. So because with that effective Hamiltonian, we also get some nice quantum Fisher informations. For now, we're ignoring the environment. So we're starting very simple. Ignoring the environment, everything is quantum mechanical. You get very nicely this quantum Fisher information that quantifies the sensitivity of your measurements. And we get very nicely n-squared scaling. But there is a caveat that it only works if there are fluctuations in the photon number. So if the photon number is fixed, and there's no variance in the photon number, there is no quantum enhancement. In fact, you want this variance of the photon number to be as large as possible. So there are two ways we can go about this. One is to truncate the Hilbert space and just fix a maximum number of photons that you can possibly achieve. In that case, you get an on-type state as your optimal state. That is just an equal superposition of the vacuum state and the maximum photon number state. The other way you can go about this is to not truncate the Hilbert space, restrict yourself to just Gaussian states, and just fix the average number of photons. In that case, the optimal state is a squeezed vacuum state, either in the symmetric or the antisymmetric modes. And that will give you also a Heisenberg term in your quantum Fisher information. Now, when I say photon number states, remember that we are working in the orthogonal, the symmetric and antisymmetric mode basis. So these photon numbers are actually rotated into that basis. If you want to rotate back into the original mode basis, these A1s and A2s, which are the physically relevant ones, they are actually not nice on states or squeezed vacuum states. They are more complicated states. So this is only in the rotated basis that you get these nice results. Now, so far we've ignored the environment. So what happens if we turn the environment on? Now the photons will interact with the environment and there will be losses. So as you would expect, it destroys everything. So in the quantum Fisher information, in front of the Heisenberg term, you will get these coefficients that are exponentially suppressing this n squared term. So here we have eta, which is the attenuation factor. When you have eta equals to 1, you have basically no environment. All the photons go through the beam splitter. At eta equals 0, all the photons are lost. And we get these eta to the n factors in there, which as the photon number goes up, this coefficient is going to vanish, making this whole term basically 0. So here are some plots of what this looks like for the on-type state on the left and the squeeze state on the right. And what you see on the top is for different attenuation factors, how the total quantum Fisher information behaves. And we can see that it starts off nice and quadratic scaling. This bottom plot, by the way, shows the scale factor. So the scale factor of 2 is what we're looking for. That's the Heisenberg term. We see that it starts off nice and quadratic. We have the quantum enhancement, but then it very sharply drops and goes back to just the linear standard quantum limit, which is the classical scaling. The worse are the losses, so the worse are your attenuation factors, the earlier this drop happens. So for these on-type states, you still have a hope for achieving this quantum enhancement if you work in a lower photon number regime, and if you can suppress your losses as much as possible. For the squeeze state, it's very similar. Your quantum enhancement will be lost due to the environment. This is basically decoherence, right? So the bigger your system is, the less quantum it will behave, basically. So the story is going to be very similar for the other strategy as well, and for all the other phases of the point spread function as well. But we are still working on it. And just to preempt the question, how does this look like in practice in the lab? I'm also curious. That's something I would also like to know. And I will be looking into that in the future and looking for actual implementations of these in the lab. But with that, thank you for your attention. Enjoy Valencia. Don't forget to come to the beach tonight. It's going to be amazing. San Juan. Yeah, I will take your questions. Thank you.
Thank you for your presentation. Is there any question?
Thank you. Thank you. Hi, thanks for the very nice talk. I know you said that it's a work that you want to do in the future, the experimental implementation, but I am now curious. Do you have any idea or any, I don't know, any suspicious on how you can implement this in the lab to be able to see the results?
Yeah, so one idea we did have is to work in the time frequency domain. So that's where they can actually manipulate these phases really well, and they do that regularly. So that's something we probably are going to be looking into. Otherwise, I'm not really sure yet. I haven't super started looking into that yet. So far, we're just looking at what are even just the minimum criteria that you need to meet to be able to achieve these quantum enhancements. So now we have an insight into that. Now we can start looking into if it's feasible, basically.
Thank you. Sounds good.
Is there any other question?
Me. Thank you for your talk. Very interesting. I have a question for the online master student. And Rajesh asked you to explain how entanglement enhances mode parameter estimation precision.
Sorry, say the question again. The government?
What?
Did you say the government? Sorry.
No.
Sorry, I misheard.
The
Can you repeat the question?
online master student,
yeah.
Rajesh is the name of the student, and he asked you to explain how entanglement.
Entanglement, right.
Yeah.
Sorry.
Enhances mode parameter estimation precision.
Mm-hmm. How the entanglement improves the precision.
Yeah.
Right, so we do need entanglement. So that is also a key ingredient. If we try the coherent state, just a simple Fock state or something, you wouldn't get a quantum enhancement. So we do all of the states, all of these optimal states that I talked about, they all include entanglement. So you're right, that's also already a prerequisite. We do need quantum entanglement, yeah.
Okay, thank you.
Any other question? Well, thank you for your presentation, Balázs.
Thank you.
The next speaker is Marco Encalaraz from University of Valencia.
Hello everybody, and thanks for coming to my talk. Today I'm going to be talking about our latest work. It's a Lagrangian theory of quantum Markovian dynamics, and as an example, its application to a laser with delayed coherent feedback. I'm going to go straight to the introduction. My supervisor gave a masterclass on open quantum systems and also with Markovianity and non-Markovianity. Just in order to sum up, I'm going to be talking about open quantum systems, right? And depending on, an open quantum system is just a quantum mechanical system that interact with an environment, right? That exchanges energy with it. And depending on the nature of this environment, we can have Markovian dynamics or non-Markovian dynamics. If the environment has no memory about its past, meaning that the evolution of the system only depends on its present state, then we say that we have a Markovian dynamics. But if the evolution of the system not only depends on its present state, but also on its previous history, then we say that we have no Markovian dynamics. And this is the one I will be focusing in this talk. Because for Markovian dynamics, there is a very, very reliable tool, which is phase-space techniques, all right, in order to solve this kind of dynamics, which consists on just taking the density operator of the system and expand it in any basis, for example, the coherent basis, as you will see later. And they try to switch from the master equation, right, the evolution equation for the density operator, to a set of equations called the stochastic Langevin equations. That are equations much more better, much more easy to work with them because they are intuitive and they allow analytical and numerical treatment, right? But for non-Markovian open quantum systems, this is not that easy because they are not local in time. So it is not that easy to apply phase-space techniques in order to obtain this set of stochastic Langevin equations that are the ones that we're interested in. So in this work, we basically fill this gap. We give a method in order to apply phase-space techniques to non-Markovian open quantum systems. So This is basically the general picture of the problem I'm going to try to solve. We have a system interacting with an environment, right? And I'm going to be considering the free evolution of the modes inside the system and inside the environment. For simplicity, I'm going to assume that there's only, well, you can see this, there's only one single mode resonating inside the system, right? Over there. And I'm also considering a bilinear Hamiltonian interaction between the system and between the environment, okay? That in the common rotating wave approximation, this just takes a bilinear shape, right? So, as I told you in the beginning, our goal is to obtain a set of stochastic Langevin equations from a non-Markovian open quantum system, right? So we're going to apply phase-based techniques, basically consist on taking the density operator of the system plus environment and developing it in a basis of coherent states. This is the Clauder-Subarsan representation, right? And then we will switch from an evolution equation for this density operator into some stochastic Langevin equations that will give us the evolution of the system. If we do all this procedure, then we get to these stochastic Langevin equations, right? And they are, in fact, quite intuitive, because you can see here the free evolution of the modes inside the system and inside the environment. And you also see the interaction terms between the system and the environment. And it's very important to note that the equivalence between this set of stochastic Langevin equations and the former, the original master equation, must be understood in the sense that any expectation value, quantum expectation value that I can compute from the original operators, from the original master equation, is equivalent, is completely equal to all the stochastic averages that I can compute from the stochastic variables in the same normal ordering, right? So you see here that these are the stochastic equations that I found for my system, and now it will be nice to work with them to try to simplify them a little bit. So you can see, for example, that the second equation that accounts for the dynamics of the environment can be formally integrated and can be plugged into the first equation, and after some variable changes, we get to these stochastic Langevin equations for the mode inside the cavity that is basically consisted of two terms. First, we have this integral over here of an object k, that we call the memory kernel. You see there the explicit expression. And then we have this other term, gamma, that you can see here, the explicit expression again, and you can see that it depends on the initial state of the environment, all right? So if one assumes that the initial state of the environment is the vacuum state, then this term over here is 0, which means that basically the whole term gamma vanishes, and we get rid of it. So then all the interaction, well, all the evolution of the mode inside the system, right, is basically told by this integral over here, meaning that all the interaction of the non-Markovian environment is contained into this memory kernel. So now that we have this equation that for now it's being quite general, I only assume that the initial state of the environment was the vacuum state, and also that the interaction between the system and the environment has a bilinear form, the Hamiltonian. Now, if I want to talk about a laser with delayed coherent feedback, as I told you at the beginning, it would be nice to take this memory kernel and try to particularize it for the problem of delayed coherent feedback, right? So picking the proper memory kernel, then we get to this stochastic Langevin equation, all right? It's just picking this memory kernel accordingly to delayed coherent feedback and then performing the integral. If you need any more details, I will be happy to discuss it later. So we get to this equation for a system with delayed coherent feedback, and it is in fact another quite intuitive equation, because you can see that basically feedback, the only thing it does is to take some information out of the system, and then the information that went out of the system at a time delay t is coming back to the system, but not affected by a phase, right? And this information that went out from the system at this time will be come back to the system again at a time delay t. So actually it's a very nice, very intuitive equation. You can see, as I told you, it gives us basically like the intuitive terms that one would just simply add classically if it's talking about feedback. But we're not going to stop here. I told you that we're going to be working. We will give an example of a laser with delayed coherent feedback. So now that we have characterized the part of the delayed coherent feedback, we now have to characterize the part of the laser. So this is the stochastic Langevin equation. We're talking about the laser with delayed coherent feedback. And so when you hear a picture of the model, but just to be very quick with this equation, the important parameters I want you to take about are this gamma, this is the cavity decay rate, but most importantly, this C over here, that gives you basically the intuition if the pumping is gaining the losses, basically. When C is greater than 1, then we say that we are above threshold, and the laser switches on. But when C is below 1, then we are below threshold, and the laser doesn't emit light, right? So this is the stochastic Langevin equation we'll be working with. We'll just have one more step. This is the same. This equation over here is the same that I just showed you. From now on, I will be talking about delayed coherent feedback. About positive delayed coherent feedback, which basically means to take this phase over here and put it to 0 so that this term is 1. And that's it. And this is the final equation that I'll be working with. So now that we have this final stochastic Langevin equation for delayed coherent feedback, and now that this equation allows numerical and analytical treatment, it would be nice to try to compute some physical quantity via analytic methods and via numerical simulations, and trying to see if this is the same result that we obtained, trying to compare them, right? So the chosen physical quantity is basically the Lasser's line width. That is just the width of the power spectrum that you can see here, the expression, okay? This takes the form of a Lorentzian. We will try to compute the width of this quantity via analytical analysis and via numerical simulations, right? So in order to try to solve this equation analytically, we're just making some approximations, okay, called linearization. And we have a very interesting result that tells us that the effects of feedback into our system basically reduces the Lasser's line width by a factor 1 plus kappa to the power of p, being kappa the product of f times t, okay, the product of the feedback parameters, and being p an exponent that above threshold, when c is greater than 1, takes a value of 2, but below threshold, when c is greater than, lower than 1, then takes a value of 1. Okay, this is the result that we obtain via analytical results. And now it would be nice to run some stochastic simulations and see if we get the same result. So I'm showing you a bunch of simulations that we did for many, many different values of C, 2 below threshold, 1 in threshold, and 2 above threshold. And for the same value of C, I've run 5 different simulations, right? As you can see, since that we are trying to obtain a power law, then this graph, which is in log-log, should be straight lines, being the slope, this exponent over here, minus p. And you can see here that actually for these different values of c minus 1, okay, these different values of pumping above and below threshold, we obtain some different slopes corresponding to this p. And maybe it gets a little more clear when I show you this graph, in which you can see all the simulations that we did, all these exponents p, these slopes over here that I computed for many different values of c minus 1. And you can see that when we start below threshold, okay, when we start sufficiently below threshold, then this exponent p takes values closer to 1. Then when we start increasing the pumping, when we start increasing this c minus 1 and we start getting close to threshold, the system undergoes a transition in which when we are again sufficiently above threshold, then this exponent, this slope over here is taking again values close to 2, which are exactly the results that we predicted via analytical solving of the previous stochastic equation. So just to sum up, we just developed a method that allows us to apply phase space techniques to non-Markovian open quantum systems. We also find that all the information of this non-Markovian environment is encoded into a memory kernel. And then we apply this framework to a laser with delayed coherent feedback, finding that the numerical results that we find are the same that we find via analytical methods. And also we find that basically the delayed coherent feedback reduces the Lasser's line width, but with different scaling laws, depending if we are below or above threshold. So that's it. Thank you so much. I'll be happy to answer your questions.
Thank you, Mark, for your presentation. Is there any questions? No one? OK, I have a question. Earlier in the slide, you put an expression for gamma.
Yes.
And you said directly that beta of T0 is equal to 0.
Yeah.
Could you explain why?
This is because, this is because if you take the density operator, okay, and you do phase space techniques, which basically is expanding this into a coherent state base, right? Giving this distribution. Okay, then if you start in the vacuum state, this is basically 0, meaning that this distribution over here, well, for beta, is basically a delta centered in 0. So then the only possible value that can take this beta over here, I wrote alpha, but I should have written beta, is 0.
OK, thanks. The next speaker is Manuel Lafonte Urbizu from University of País Vasco. Are you here? Yes.
Well, hello everyone. I hope you're enjoying the Congress so far. Well, here, my name is Manuel, they already said, and I'm from the University of the Basque Country. I'm here to present you towards AI-driven scalability in multi-mode superconducting quantum processor design. So, in order to be all on the same foot, first of all, when we are designing superconducting circuits, we are going to give a brief crash course on superconducting circuits, right? We try to get the Hamiltonian. Hamiltonian is composed of the kinetic part and the potential, right? So, in an electric circuit, in a superconducting circuit, we have three elements. First of all, capacitors, which account for the kinetic part, and are described by the number, the n operator, which accounts for the number of Cooper pairs on our system, and could be more or less equivalent to the momentum. And the other two are a linear inductor and a non-linear inductor called a Josephson junction, which contributes to the potential of our Hamiltonian, and it's described by the phi operator, which accounts for the magnetic flux on the system, and could be more or less equivalent to the position. So the Josephson junction, this new electric element on our system, is very useful because, as I already said, allow us to have a nonlinear potential, which results in energy levels that are not equally spaced. So that will allow us to, in theory, make a good qubit, right? So what's the goal of our talk? Our talk we'll try to design a multi-qubit quantum processor that's more resilient to noise than the hardware we already have. So in order to do that, first we have to define what is a good qubit. A good qubit for us will be trying to extend the coherence times that we are dealing with. We have two coherent times, T1, which accounts for the bit flip noise, right? And T5, which accounts for the phase flip noise. The T1 will depend on the overlap between the logical states of the qubit, and the phase flip noise will depend on the dispersion of the energy with the parameters of, with the sources of noise of our system. In this case, the environment can affect our qubit with charge noise or flux noise. And also, on the other hand, we want to have coherent and fast control. We have to be able to control our qubit. So we are demanding a large harmonicity in order to have distinguished selective control of our energy transitions, and also a high frequency of our qubit in order to, apply the rotating wave approximation, right? Now, the vast majority of the current hardware is single-mode qubits, which they have 1 degree of freedom, and that makes basically impossible in the majority of the systems to address these two types of noise at the same time, the bit flip noise and the phase flip noise. For example, in the Transmon, it's immune to dephasing, but it's not protected against bit flip noise, achieving coherence time of about 200 microseconds. We can see that here in this example. For example, these are the two wave functions of supposed qubit circuit, which is protected against T1 bit flip noise because they are not overlapping. But as we see, they are very narrow, so are very dependent on the flux in this case. And the other one, the T5 protected, which is the phase flip. The phase flip. In this case, they are not so much dependent on the variation of the flux noise, but they are overlapping, so are not protected against the bit flip, right? So, what's one way to tackle this problem will be with multimode qubits. That gives us extra degrees of freedom, so we can allocate these requirements, and they can coexist. We can see that here. Basically, we are having these energies that are not very much dependent on the external sources of noise. This would be n or phi in each of case. And here, this is the most important one. Here, since we have an extra degree of freedom, we are basically unlocking a new dimension where we can allocate this other wave function. So both are extended in the parameter space, but now they do not overlap because they have an extra dimension where they can be. The trade-off of this approach is that this is a little bit of a mess because its degree of freedom introduces a infinite dimensional Hilbert space. So tackling this problem with simulations, which is what we are doing, is very difficult. And so since we are embedding the properties of our system in a Hamiltonian, we have to diagonalize that Hamiltonian to get the properties of our system, and that will be our bottleneck. So how are we addressing this? We are going to take an algorithm, an evolutionary approach to this problem, which is a differential. The algorithm is called differential evolution, which is a type of global optimizator, basically, and it's a population-based optimizator. So what does that mean, right? We will have our circuit with the parameters of our components, and we are going to map those components into a vector, and that vector is the so-called individual or solution, and then we will make a bunch of them, and that will be our population, right? Easy. So the whole algorithm, without entering much detail, will be basically have our population. With that population, we will make a mutated vector, which is a mix of 3 different vectors of our population. Then we will make a new trial vector with randomly selected vector components of the old vector in our population and the mutated vector. And we will evaluate this trial vector against the old vector, and if it's better, we will keep it, and if it's worse, we will discard it, basically. We have checked that this approach is good because our colleagues in Bilbao have reached a new type of superconducting qubit, the so-called Fluxmon. This new type of qubit is a multimode qubit, which achieves large harmonicities of a third of the qubit frequency, so we can apply the rotating wave, and longer coherence times of about doubled the estimated coherence time, since this is all in simulations, but about double the Transman coherence times, right? So the evolutionary approach is promising, at least. Now, our approach, what I am doing, is a little bit different. In this case, we're trying to design a 2-qubit processor instead of 1 qubit that we will connect or couple to each other. We will design a circuit that is already behaving like 2 qubits. What do I mean with that? We will design a system, a 4-level system, and we will identify its level of energy as if it were all 2 qubits. So the 0, the 0, 0, 0, 1, etc., right? And that's another approach that hopefully enhances the connectivity or solves other problems, right? Now, optimization. What we are demanding on our system. Well, our cost function, we will, in our cost function, we will tackle 3 different problems. We will demand a large harmonicity that will allow us to have selective control and excite the energy transitions that we want, instead of several energy transitions. Also, we have to be protected against noise, right? That's the whole talk. We will demand that we have low energy dispersion, so we are protected against phase flip noise. And lastly, we want to make our qubit protected against bit flip noise, but not so protected that we are not able to control it. We have to search for a balance between protection and controllability, because if our qubit is completely inert to the environment, we are not able to make changes in it, right? So we are looking for something about 0.5 of the element transition matrix. And now our results. These are the results. Right now we are trying to understand how this kind of system behaves. So this is a very, very simple case. But still, we have reached some good results. In this case, we are working with a circuit that has one extra degree of freedom. So it's a multimode with 2 degrees of freedom, and we are looking with the 3 different parameters that we have talked about. And this specific circuit reaches, well, these are the transition frequencies between the energy levels. And we can see that here, that we are achieving a minimum harmonicity of more than 90 megahertz that will, in theory, allow us to control our qubit selectively and excite the energy transitions that we are tackling, basically. Then here we see the energy levels. The energy levels against external source of noise, in this case the charge. We see that the energy levels are basically inert against this type of noise, resembling the characteristic transmon protection against the phase flip. And the only one that's a little bit affected by this type of noise is the last energy level, but that will be our leakage channel. So we are not so much worried about that. And lastly, the transition element matrix. Here, our results are not that good. Okay, we demanded that our results were about 0.5, as you remember, and as we see here, the elements are about 1.5, being the most worrying one. This one here, the 3 to 4, since 4 is our leakage channel. So that will be our next task to tackle this in the very near future. We will address this issue and update our cost function. And this suggests that maybe we are exploring a circuit that is not rich enough or has the modes necessary to tackle all these problems at once. So maybe we have to extend our system to a larger one, right? And yeah, in the super distant future, we hope, we will try to extend this paradigm to more qubits, basically. Scale this to even more than 2 qubits, 3, 4, much more qubits. And in order to do that, we are going to make a different approach and trying to train a machine learning model that will, in theory, predict the topologies that have good properties before the diagonalization. If you remember, the diagonalization of our Hamiltonian was the bottleneck. So if we could avoid the diagonalization of the Hamiltonian before doing this, the diagonalization of the Hamiltonian with the machine learning, basically, the model will predict if the candidate is promising, and we will diagonalize only the promising candidates. But that's our long-distant future. Thank you very much. I hope you enjoy it. These are our collaborators here, my supervisor, Mikel Sanz, and Pablo Garcia, the designer of the Fluxmon. And yeah, I hope to see you all in San Juan this night. So thank you very much.
Thank you for the presentation. Is there any questions?
Thank you so much for the beautiful talk. So just technical question about this genetic algorithm that you use. So it's, as far as I know, this is a bit of a, like one of the elders, let's say, one of the old algorithms that people used to use for this type of problem. So can you expand a little bit about why did you choose this one? What is the advantage of it, and whether you can fall into trouble like falling into yeah, it's a non-convex problem, right? So you can fall into minima that are not the real ones, and what's the
good question. Thanks. We chose this approach because this is a global optimization method. So as we see, this parameter of space is very large, and the diagonalization of our Hamiltonian is the step that will evaluate the cost function. This evaluation of the cost function requires a diagonalization of the Hamiltonian. So we have to avoid as much as possible the evaluation of our cost function. So we take this approach because since it's a global optimization method, it will explore the parameters of space with a randomized seed, if you want. And then we will polish our solutions in order to reach the actual minima. Probably we are not in a global minima, but probably that's not required. Maybe the solution that this global optimization method is achieving is good enough for us. And since we can explore the large parameter of space very rapidly because we are taking so many points instead of a gradient that has to evaluate each point, this avoids the evaluation of the cost function as much as possible, which is the thing we want now.
Thanks. Can I ask a follow-up?
There's another question, but he has the QR already.
Yeah, okay.
Hi, hello. Thank you for your presentation. I like so much because it's regarding to Johnson, and I have many questions regarding this. First of all, you show a circuit, Johnson with a capacitor and inductor. I want to know regarding the Hamiltonian, if you use some method for use quantization for this circuit that you show?
Yeah, there is a standardized way to quantize superconducting circuits, which is, well, I can show you here. Okay, this obviously is a very, very simplified version of it. But yeah, so we will demand, there's, okay. Basically, we have two operators that are the number of Cooper pairs, if you want, and then the magnetic flux. And since these are more or less equivalent to position and momentum, we can take the formalism that's already done in quantum mechanics and extrapolate it to this kind of circuits or system. And basically, we will demand, sorry if the sign is wrong, I always make this the other way around, but something proportional to I, okay? This is the canonical quantization of the quantum mechanics. And we will make this when we have our Hamiltonian. The actual Hamiltonian is a little bit more complicated, but just a grasp of it is basically taking the capacitors, arrange them in a matrix that accounts for the connectivity of the different elements. So the more precisely, I didn't say that, but the nodes are actually like the positions of our system. The nodes are where the elements are being connected. And the flux is basically the magnetic flux that's going through the system, right? So yeah, if you take this, then make a matrix with the different elements and make that matrix in the Hamiltonian and take this quantization, then you get your quantized superconducting circuit.
Okay, thank you. And another question I have regarding the selection of this. Your project is theoretical, or actually you can achieve a physical component?
Okay, very good question. We are doing only simulations, but the simulations are very much focused on fabrication. So when we optimize the system and we look for answers, solutions, the bounds of our optimizer are bounded to the actual elements that we can fabricate nowadays. So this is a very restrictive problem because we are not allowing the system to search for an unreal set of parameters. So that's very complicated. But yes, and in fact, if someone wants to fabricate the Diffluxmon, it's very welcome to do so. Yeah, the parameters are fabrication addressed, fabrication ready.
Yeah, and regarding this material that in the future you are thinking to use some type of superconducting like neodymium on aluminum. Are you thinking in this way, or it's not yet selected?
For now, I'm not so familiar with the actual experimental setting of the different superconductors, so I'm not able to answer the question. But
okay.
yeah, I guess that the parameters we are using are more or less exploring all kind of options.
Good, good. Thank you.
Sorry, we have to go to the next speaker because of time. So thank you for your presentation again.
Thank you very much.
The next speaker is Juan Daniel Torres Luna from Delft University of Technology.
Well, hello, everybody. It's a pleasure to be here at Valencia, and it's a pleasure to share my research with you, which is about building parity qubits using Pur-Mens-Majorana modes. This is a collaboration between theory and experiment. I'm working in the theory side, so I will be sharing those results with you. So first, as a motivation, we have been discussing a lot about quantum information in qubits, and to me, it's very exciting to see the experimental progress in different platforms that can achieve increasingly complicated devices. Ultimately, we just want to have single qubits, but we want to have millions of them. So it's exciting to see how different technological platforms, such as superconducting qubits or spin qubits, increase the number and the complexity of these devices. However, today I'm not going to talk about a many-qubit device. Today I'm going to talk about a single qubit. And in order to build some intuition about it, I'm going to start talking about a very simple type of qubit, which is the charged qubit. The charged qubit is just having an electron charge into quantum dots defined on some semiconductor. As you see here, that charge can be either in the left or in the right, and that will be your qubit states. These two states are coupled by a hopping T, and all these parameters can be controlled with an electrostatic gate. The parameters that are relevant in the system are the energy detuning epsilon, which basically tells you if the electron is in the right or in the left state, and the tunnel coupling between them, which determines the hybridization between them. This is a very old experiment from 2004 already, and they teach us a very important lesson about charged qubits, and it's that they are very, very noisy. In the following plot, you see the main result of that paper, and that is the probability of being in the left state. You can see that as you move in the y-axis, the detuning, you quickly decohere, you quickly collapse to being either on the left or in the right. You lose all coherence. But if you are in the middle, you can achieve some coherence by being in the sweet spot of this charged qubit. However, if you look at the x-axis of this plot, the scale is very small. This is 2 nanoseconds, and having a coherence time in that order, it's not really useful. So with this in mind, we come to the fundamental problem that all qubits have, and it's that you are trying to couple and control a system, and at the same time, you're trying to maintain that system isolated from everything else. So the same mechanism that you're using to couple is perturbing your system. And this is always a trade-off that we find in qubits. And here I list some coherence and relaxation times for different types of qubits. And you can see that the charged qubit is actually the worst of them. Spin qubits are kind of better, and transmons are the most developed experimentally these days. So with that in mind, we come to the research question. how can we design a semiconducting qubit that is actually robust against noise and against decoherence? And to answer that, the answer comes from condensed matter physics, and it's actually topology. The answer is Majorana-bound states, which are the ground state excitations of a topological superconductor. In 2001, QTYR found that in a p-wave superconductor, you can have a topological state. So this means essentially that in a superconductor, you have a spectrum that is symmetric with respect to positive and negative energies. You have electrons and you have holes. When you are in a topological phase, however, you have one extra state allowed in that system, and that extra state is bounded at 0 energy. Because of particle-hole symmetry, you cannot have a single state, so you need two, and therefore you have two states at 0 energy, and they correspond to a pair of Majorana-bound states. The crucial thing about these states is that they encode a single fermion, and they are non-local. This single fermion is separated in space, and it lives in two different parts of the universe. If you couple to one of them, you cannot actually change the state of this fermion. The problem about this is that p-wave superconductors are rather difficult to find in reality because they are spinless. And as we know, electrons have spin. So people thought about it for some time, and they came with a few proposals. The one that I will focus on is minimal QTYR chains. But if we look at the QTYR model for a moment, we imagine that we have a chain of 3 spinless fermion. If we decompose this chain into the Majorana basis, we are basically duplicating each fermion into 2 Majoranas. And rewriting the Hamiltonian in this basis, we obtain something with 3 terms. You can forget about the equation for now and just see a dot plot on the right side with 3 colors. Each one of those colors is a different interaction. If we look at the shape of those terms, we can see that several of them can be tuned to 0, actually, if t and delta are equal to each other and if mu is equal to 0. And if we are at that regime, we achieve something that is called a sweet spot, where the first and the last Majorana are decoupled. And in this sense, they form one fermion that lives in 2 separate parts of the universe. Well, people have thought about this in experiments for a long time. And recently, they managed to fabricate, in semiconducting nanowires, these QTYR chains. They fabricated something that is called the Pullman's Majorana, and that is the smallest system with Majoranas that you can find. And it's just 2 quantum dots with an Andreev state in the middle. Here you can see how that Andreev state looks like. It's inside of the superconducting gap. And what it does is that it mediates processes between these 2 quantum dots. So it can mediate cross-Andreev reflection, a Cooper pair appearing in the 2 quantum dots. And it can mediate elastic tunneling, which is just like in the charge qubit, an electron going from left to right. By tuning this Andreev state, you can reach the sweet spot where the 2 interactions are degenerate, where you have this crossing and you have a ground state degeneracy between even and odd manifolds. Once you tune to this system, you have some degree of protection, but you don't have full topological protection. This protection gives you robustness against the tunings of individual quantum dots. That is, one Majorana in one side will be protected against things happening to it. And the way that we see that is by detuning, in this case, the right dot, and seeing that the zero bias peak, which is the signal of Majoranas, remains. In the same way, this protection is broken if we change the 2 quantum dots simultaneously. If we globally perturb the system, we transform this essentially into a charged qubit, which, as we know, it's pretty bad. Anyway, now that we have this building block, we need to remember that this is just one fermion. And in fermionic systems, parity is protected. That means that electrons don't just randomly appear. Their parity is protected in superconductors, which means that electrons always come in pairs. So that means that you will have either an odd or an even number of electrons globally in your system. In order to have the minimal qubit, we need 2 minimal QTYR chains. And by combining their ground states, we can have even, odd as the qubit states, or the complementary states in the odd parity sector. Once we have this, we define the minimal type of qubit, which involves 2 minimal QTYR chains with a quantum dot in the middle. This quantum dot will be the only part of the system that is non-protected, but this will always remain empty. It will just be an effective tunnel coupling between the 2 QTYR chains. And if we look at how this looks in the block sphere in the qubit space, what happens is that along the z-axis, we have the parity states, even, and odd, odd. If we want to do rotations from z into x, we need to bring the middle dot into the game and couple the two chains, and that will allow us to create a superposition of two parity states. If on top of that we want to do rotations again along z, we need to detune the chains and reach the regime of the charge qubit. Well, the effective Hamiltonian of the system in this sub-energy space looks like this. It's a qubit Hamiltonian with a sigma z and a sigma x type of terms. And now let's discuss briefly how people actually manipulate these states. So what they do is that they initialize the system into some parity states. They measure it there. And then they detune the parameters by sending pulses into some fridge with some cables. And then they achieve this coupling via the middle dot. They couple the two key-type chains. Then they cancel the pulse, they decouple, and then they measure. That is how these experiments are performed. But I'm not going to talk about experiments. I can just run this into a simulation. And a critical detail of the simulations is the fact that things are messy, that there is disorder. But luckily for us, I'm going to focus on quasi-static disorder, which just means random fluctuations of the parameter in a time scale that is longer than the measurement time. So it's just like adding a random Gaussian variable to all the parameters of the system. And that affects the qubit frequency. And consequently, it affects the return probability of the system. So we will have fluctuations in the amplitude and in the frequency of these oscillations. But because this is Gaussian, we can integrate over all noise realizations. And what we find is that in this system, you can achieve Rabi oscillations. That is, you can coherently go into the XY plane of the block sphere by using the middle dot. So what's happening here is that we start from a decoupled configuration. Then we bring the middle dot to some chemical potential above resonance, and we see that the ground state of the system starts to oscillate between even and odd. However, we also see some fuzziness and some noise on it, and it's particularly pronounced in the bottom part of the plot. That is when the middle dot is closest to resonance. That is when the charge is the closest to be occupied, and in this regime is when the middle dot actually behaves kind of like a charged qubit and limits the coherence of our system. However, if we are far enough from it, the limitation is no longer the middle dot because that one is far away. The limitation in that case is these poor man's Majorana states. So doing this type of Rabi experiments also allow us to explore in more detail what protection means. So I mentioned that if you detune a single quantum dot, the qubit frequency or the zero energy states will not change. And if we do that, in this case by bringing the dot to some fixed coupling and detuning one of the chemical potentials, we see that the Rabi oscillations persist. We see that there's some small dependence on the frequency, but we see them persist. And in the same way, if we detune the two quantum dots, we go to a charged qubit regime where, basically we lose all coherence really fast because basically we're transforming these protected states into just a regular fermionic state. Well, just to look at it in a bit more detail, we can answer the question if this is better than a charged qubit. And in fact, it is better because it has a stronger sweet spot for the two sides. And what I show here are oscillations at two different middle dot potentials. And you see that when we are close to resonance in the left plot, the oscillations decay faster than when the middle dot is far away. This means that if you are far away from resonance, the actual limiting factor is the chains. So, well, the last thing that this allows us to conclude is what happens when you extend the minimal key-type chain to a longer chain. So in this slide, I show different lines for different lengths of the chains. I started with a PMM with 2 sides, and then I show 3, 4, and 5 sides, and it keeps extending. So what I do is that I calculate these Rabi oscillations, and then I just simply fit and I say, okay, what's the coherence time that I will find, and what is the qubit frequency that I will find, just by looking at these decaying oscillations. And the first thing that I found is that as I move away from resonance, as my mu-m is bigger and bigger, the frequency decays because the oscillations become like longer. But it kind of saturates at some point, so you can see that the change between 150 and 200 is not that big. But on the other hand, if you look at the T2, at the coherence time of this qubit, you can see that as you increase the length of the chain, there is a dramatic increase in the coherence of these qubits. And actually, for longer chains, increasing the chemical potential from 150 to 200 gives you a very significant increase in coherence, which means that if you have a longer chain, you will be able to perform hundreds of coherent oscillations before you actually decohere. So this is something that is exciting and promising for this research. So as a summary, yes, parity qubit made of Pullman-Majorana is actually better than just a charged qubit because there's a degree of protection coming from the Majorana excitations. In a PMM, it's quadratic, but as you make the chain longer, the protection increases. If you are closer to resonance, the limiting factor is the noise in the middle dot. And we find that if you make chains longer, the improvements that you will find in coherence are promising to have to be able to do several coherent operations before you actually decohere. And with that said, I thank you all for your attention.
Thank you for your presentation. Is there any quick questions? Could you pass the cube, please?
Hello. Great talk. Juan, I was just wondering about the last part of the T2. This is the T2 against the chemical potential of the middle quantum dot, right?
Yes.
But why is it different when you extend the chains? Because it's just like a weak link. It's a local perturbation of the coupling between the chains.
Yeah.
I expect that the T2 will change when increasing the chains for the chemical potentials of the quantum dots of the chains, but not in the middle.
So what happens is that you can think about the middle chain just as an effective tunnel coupling between the two. In this plot, for example, if you are close to zero, close to resonance, that means that they are strongly coupled, so you have a really fast oscillation between them. In this regime, because the dot is almost occupied, you are the most susceptible to charge noise in the middle dot, which is not protected, as you see in the bottom part of that plot. If you go higher, if you go farther of resonance, it means that the coupling is weaker between the two chains. But it means that you are also less sensitive to noise in the middle dot. If you are far of resonance, at that point, the limiting factor are the chains themselves. So if the limiting factor is the chain, going to a longer chain will improve that limiting factor.
Regarding great talk, Juan. Regarding this tuning of the middle dot, how much can you tune it? How far away from that coherence can you go? Because if you completely detune it, you put, I don't know, 1 electron volt for sure. Then the limiting factor is the Pullman-Majorana's length, but you cannot decouple the chains. So there should be another sweet spot there, no, to choose. How far can you actually go with that scale?
I guess that you want to find an off regime where they are coupled. I mean, they will not be never fully decoupled because there will always be a second order process. It will just be canceled. And it means that you have a rotation, but it's very, very slow. So that would be the off point. And then the on point means bringing it closer to resonance, depending on which one you choose. So I don't know if that answers your question.
My question was more like, you can detune this mu-m to whatever you want. No, you actually cannot do that in an actual experiment. So what's the limit? How is it realistic to put that mu-m at 300 microelectron volts, or is that too much to consider?
Yes, so in a real experiment, what will happen is that you will have another resonance in the middle dot by the next electron that could live there, and that will be a few millivolts away, a few milli-electron volts. So,
okay, so
this is still within that window.
Okay, perfect. Thank you.
Thank you again for your presentation, and thanks to all of the speakers for these interesting talks. Applause.
Thank you.